Assalamualaikum and hello everyone. We are from Group 3 and this is our report presentation of Experiment 3, which is Vapor Compression Refrigeration. Our group have 5 members and this is the list of our group members. Introduction. So as you can see, there is a figure 1, which is the image of the vapor compression refrigeration cycle. We start with compressor, which is the start of the cycle. The compressor compresses the refrigerant gas, making it hot and high pressure. This step adds energy to the refrigerant. Second, condenser, which is the heat rejection. The hot gas goes to the condenser, usually at the back of your fridge or outside your aircon. Here, it releases heat to the surrounding and becomes a high pressure liquid. And then, expansion valve. This is where the pressure drop. The high pressure liquid passes through an expansion valve. The pressure drops suddenly and the refrigerant becomes a cool, low pressure mixture. And then lastly, the evaporator. This is where the cooling happens. The cold refrigerants enter the evaporator inside the fridge or rooms. It absorbs heat from the air inside, making the space cooler. The refrigerant evaporates back into a gas and the cycle repeats. According to the second law of thermodynamics, heat won't move from cold to hot on its own. We must do work to make it happen. The system's efficiency is measured by COP, which is coefficient of performance. A higher COP means better performance. When we have a better performance, it can remove a lot of heat using only a small amount of refrigerants and very efficient, especially at a larger scale. And it can cool things below room temperature without needing extra energy at the cold end. These are the examples that we can find in our daily life, which are the refrigerator, the aircon, the automobile air conditioning system, and the water coolers. The objective of this experiment is to determine the coefficient of performance, COP, for vapor compression cooling system. And the scopes for this experiment is first, water was used as the medium of evaporation and condensation process in this experiment. And then the second one is all the required readings were taken each 10 minutes. The reading is thermometer readings, flow meter, watt meter, condenser and evaporator pressure reading. And then the third one is the water flow rate of evaporator was set to always maintain at 25 gram per second. And lastly is the water flow rate of condenser was varied in the range of 35 to 40 gram per second in turns until 4 readings are obtained.
So next is the theory part. So in this experiment, we are focusing on the second law of thermodynamics and the coefficient of performance, which is COP. So first, the second law of thermodynamics says that heat will naturally flow from a hotter body to a colder one. However, in this experiment, the refrigerator and the heat pump reverse this process by using work, which to transfer the heat from a cold to a warm space. Next is the coefficient of performance, which is COP. COP of a heat pump or refrigerator is a ratio of desired and useful output to the amount of work or energy input. So it used to measure the energy efficiency. So next, we are deriving the formula of COP for the heat pump and refrigerator. For the heat pump, it is QH over work done, which is W. So we can get TH over change in temperature between higher and the cold space. So for the refrigerator, the formula is QC over W, work done. So it is equals to TL, which is lower one, over the TH minus TC. So we can refer to the figure on the left side. So the conservation of energy principle for the cyclic device is shown as W equals to Q1 minus Q2. So the final formula for this experiment is Q2 over Q1 minus Q2.
So for experimental setup, for the right side, so we can see got the evaporator pressure. We can measure the evaporator gauge pressures, and for the tube is the evaporator water flow meter. So from there we can measure T1, T2, and T3. So at the left side, we got the condenser water flow meter, which is the tube, and the condenser pressure. We can measure the condenser gauge pressures. And the middle here is the watt meter to measure the power input. And so below here is to measure the T7s. And at the same time, this is the valve. So when the valve is open, it's vertical, and when the valve is closed, it's horizontal. So the below one, which is the white color one, is the main switch. So this is the figure of refrigerator, a refrigeration cycle demonstration unit R633 PA Hilton. So for methodology, the first one is we open the valve. So open the valve from horizontal to verticals. And the second one is we open the water pipe and set the evaporator flow meter to 25 gram per second. After that, we set the condenser flow meter to maximum, which is in the experiment is 50 gram per second. After that, we switch on the main switch, which is the white color one, and wait for the system to cooling and stable within 10 minutes. So after waiting 10 minutes for the system to cooling down, and we record all the results such as the absolute condenser, condenser gauge pressure, absolute evaporator, evaporator gauge pressures, and the compressor power input, and also T1, T2, T3, T4, T5, T6, T7s. So after that, we repeat 4 times. So we change the condenser flow meter in between 35 to 14. So the first one is 15, which is the maximum, and the second one is in this experiment we use 38, 37, 36, and 35. So we only change the condenser flow meters, and other that we didn't change. So we might make sure the absolute evaporator, which is constant at all time, which is the 25 gram per second. Okay, so after we repeat 4 times and we record all the result in the table. After that, we switch off the main switch, which is the white color one, and cross the water pipe. And the last one is we cross the valve. So cross the valve is from the verticals to horizontal. So this is the overall experiment procedure.
As for the result, we are remaining the absolute evaporator to 25 gram per second while changing the absolute condenser to 50, 38, 37, 36, and 35. And then we can record all the data we want, which include the pressure and all the temperature. By using all this data, we can calculate the rate of heat transfer at the evaporator and the condenser. So when we have these two data, so we can calculate for our coefficient performance, which is COP.
For discussion one, the question is calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 test run and discuss the result. For the first equation is the rate of heat transfer at evaporator equals to the mass of flow rate, which is M, evaporator multiplied by the specific heat capacity C of water multiplied with the temperature 1 minus temperature 2. And for the condenser part, which is mass flow rate minus multiplied with specific heat capacity of water multiplied with temperature 3 minus temperature 4, which you will get the rate of heat transfer at condenser. For equation 3, which is the since both QH and QL are defined as magnitude and hence are positive quantities, therefore coefficient of performance of refrigerator goes to the multiples QL over work net, which also equals to the QL over QH minus QL. QL is the rate of heat transfer at the evaporator, while QH is the rate of heat transfer at the condenser. So for the this shown that it's the manual calculation using the formula given in discussion one, the first page, which is the rate of heat of transfer at the evaporator, condenser, and also the coefficient of performance COP refrigerator. So as you can see, this is the manual calculation of test one example. We got 0.0836 kilowatt for the rate of heat transfer at the evaporator, while the at the condenser is 0.1254 kilowatt. And also the COP, which is the coefficient of performance, we got 2 using the formula given. And yeah, for using the manual calculation, we can get the test one test number run from 1 to 5 of the rate of heat transfer at evaporator in kilowatt and condenser, and also the coefficient of performance COP. From the observation, we can see that the rate of heat transfer at the evaporator is higher than condenser. This is due to the evaporator, which is heat is supplied to the liquid, causing it to change from a liquid to a vapor state. And also a greater amount of energy is needed because gas particles are more widely spread. And also for the condenser part, where heat is extracted from the gas, causing it to condense into a liquid, which you can refer to the reference number 5 at the reference part. We also can see that the COP at test run number 1, 2.0, is actually relatively low to be logically. This could indicate a poor system performance or harsher operating conditions. And so we also can see the consistent of higher COP values 4.5 to 6, which most of the values are 4.5 or 6, which also consider as they are in the stable conditions and system perform efficiently and consistently.
Okay, my name is Imam. So I will be presenting the discussion to explain the effects of changing the condenser flow rate of T1 and T6 to compressor power, and draw the graph and discuss the result then. So here's the graph. As you can see, the provided graph shows the relationship between condenser flow rate measured in gram per second and various temperature points T1 and T6 in what appears to be a refrigeration or HVAC system. Examining this data reveals several key points. Okay, for the first one, which is T6, the orange lines, which has highest temperature, represents the compressor discharge or condenser inlet temperature, ranging from 33 degrees Celsius at 50 gram per second to 35 degrees Celsius at lower flow rates. T5, the light blue line, lowest temperature, likely represents the evaporator region temperature, increasing from approximately 18 degrees Celsius at 50 gram per second to 21 degrees Celsius at a lower flow rates. T1 until T4, the remaining lines, show intermediate temperature between 27 until 30 degrees Celsius that increase by 1 until 2 degrees Celsius as flow rate decrease. Condenser flow rate and temperature. As the condenser flow rate change, it has limited impact on the temperatures T1 until T6. Especially T1 and T2 show a slightly increase as the flow rate decrease, while the others remain relatively stable. Okay, for the graph of compressor power input against the absolute condenser, as you can see, the graph illustrates the relationship between compressor power input in watts and absolute condenser values in grams per second. From 35 gram per second to 40 gram per second, the compressor power input increases from approximately 217 watt to 220 watt. From 40 gram per second to 50 gram per second, the compressor power input increases slightly from 220 watt to approximately 221 watt. Overall, Manipulating the condenser flow rate influence both the temperature profile within the condenser, especially T1 and T2, and the power consumption of the compressor.
In conclusion, this experiment aimed to determine the coefficient of performance (COP) of a vapor compression cooling system. The results show that the condenser flow rate decreased in each test, while the evaporator flow rate stayed the same. The pressure remained steady and the compressor power slightly decreased over time. The COP values for the condenser flow rates of 50 gram per second, 38 gram per second, 37 gram per second, 36 gram per second, and 35 gram per second were 2, 4.63, 6.62, 6.58, and 4.10, respectively. The heat transfer at the evaporator and condenser showed the system was properly cooling and rejecting heat. The COP varied, indicating that the system performed best under certain conditions. We observed that as the condenser flow rate increases, the COP also increases. Additionally, when the condenser flow rate decreases, the system's temperature tends to rise. To improve the experiment, we could calibrate the equipment, insulate the setup better, and repeat the test for more accurate results. Controlling the environment around the system could help reduce small errors. In summary, the experiment showed how the vapor compression refrigeration system works and how small changes in pressure, temperature, and flow affect its performance. With a few improvements, the setup can be better for future experiments and learning.
So for the suggestions, we can see that to address the suggestions to address any flaws or improve the experiment, we refer to the reference 7 and 8. Firstly is the calibrate instrument properly, where ensure all measuring tools are calibrated to reduce errors to and get accurate results. We also need to control the environment conditions and also keep the ambient temperature constant and insulate the system to prevent external influence. You also need to repeat the test, run more trials to reduce random errors and get more reliable average results. We also need to improve system insulation, insulate pipes and components better to avoid heat loss or gain that affects results. Lastly, we also need to study refrigerant properties, analyze the refrigerant properties, example enthalpy, specific volume for deeper insights, so to avoid errors. As for the safety procedure, we have consists of three parts, which is the pre-experimental handling, during experimental handling, and post-experimental handling. For the pre-experiment handling, firstly is to open the main switch with dry hand to avoid electric shock, and also we also need to open the valve completely, the middle valve, the yellow valve, for the condenser and middle valve, because just to avoid overflow or leakage. And also we also need to not turn on the power supply until all checks are completed, just to avoid any misfunction. And also during the experimental handling, no manual adjustment. Avoid any manual adjustment, as avoid adjusting valves or electrical parts while the system is running. It might cause some dangerous connection costs. And also for do not touch the pipe and compressor when the process occur, because it's very hot, which might hurt our skin. And monitor the pressure gauge at all times. Continuously observe the suction and discharge pressure. Never let pressure exceed rate limits, which might cause leakage or explosion through the pipes. And for the post experimental handling, switch off the main switch. Okay, we do remember always, after finish the experiment, remember to switch off the main switch to avoid electric circuit shock. And also wait for 1 minute while we close the water pipe source, just to calm, to wait for it to calm before everything was closed.
So this is the reference that we use for this experiment. So basically got from the reference from the textbook or from the website internet. That's all for our presentation. So thank you, doctor.